Okay. Now g of f of x is, of course, f of x squared, which is the square of the square root of x minus 3, which is x minus 3. Now you can put any number at all in for x minus 3, but that doesn't mean that g of f of x has an unrestricted domain. Just because the domain of this expression is unrestricted doesn't mean the domain of this one is unrestricted. The reason being that this function means you take x and you do f of x first. Okay, and f of x is the square root of x minus 3, and the domain of f of x is just x values that are greater than or equal to 3. Anything less than 3, you're going to have a negative under the square root here. And just because you're squaring it and the square root sign goes away doesn't change the fact that you can't put 3 in for x because your function is g of f of x. Okay? So, since you're squaring f of x, you can't put in numbers less than 3 because f of x doesn't have a value for numbers less than 3. Then, same thing here and same thing here. Even when you get down here, x still has to be greater than or equal to 3 to satisfy the domain restriction on f of x. Now that's a little harder than just the substitution. And when you come down to it, the substitution is your bottom line. That's the thing you really got to get. But you also are going to be expected to be able to address the question of domain. Okay. For this composite, notice that g of x requires that x be greater than or equal to 0 because g of x is the square root of x. You can only take square roots of non-negative numbers. So, when you do f of g of x has to be greater than or equal to 0 because you're doing g of x. Okay? And that works out just fine. Now, the final result that you get is just x, and of course there's no restriction on the numbers you can put into the expression x, but since there's a restriction on g of x, that restriction follows through this composite. G of x is greater than or equal to 0, so f of g of x, you start by putting x into g of x, so you have to put only non-negative numbers in for g of x. G of f of x, and I actually didn't write this down carefully enough, because there's a technicality involved here. It's not really a technicality, it's important. That's the square root of f of x, which is the square root of x squared, which I said is x. And that's not really quite right if you don't restrict the domain. And there's no reason to restrict the domain here because all you're putting in to g of x is values of f of x, and values of f of x are always 0 or positive. X squared can never be negative, so you're never going to be putting a negative into the g of x function. So this is perfectly good. Okay, but the problem with that is just nothing wrong from here to here, but the square root of x squared really isn't x. For example, what's the square root of negative 2 squared? Let's say it over here, square root of negative 2 squared is the square root of 4, which is 2. It's not negative 2. Okay? So, if x is negative 2, g of f of x would equal the square root of negative 2 squared, which would be 2, but that's not x. X is negative 2. If you plug that into this, you don't get negative 2, you get 2. So I was a little careless when I wrote that down. The square root of x squared is the absolute value of x. That's a little bit of a subtle point, but just take this example. If x is negative 2, the square root of x squared is 2. That's not equal to x. It's equal to the absolute value of x, because x is negative 2. Absolute value of negative 2 is 2. So, another point that you want to be clear on. Still, there's no restriction on the x value. You could perfectly well put a negative x value into this. Again, a negative x value into f of x gives you the square, and that's going to be all right. and that's going to be a positive number or 0. And g of that will be the square root of that number. Since the number isn't negative, since f of x isn't ever negative, that's not a problem. You can always do this. So the only thing I want to change about what I said in class here is that the square root of x squared is the absolute value of x. It's not x.